Okay, now we're going to take a look at some basic wave measurements and quantities. To be honest with you, most of these you should be familiar with. You should have seen them before. Okay, so we're going to define the quantities used to describe wave motion, namely frequency, wavelength, amplitude, and wave speed. We're going to derive a relationship where v, the wave speed, equals the frequency times lambda, the wavelength. Okay, so these are basic measurable length-based quantities. Amplitude, as we looked at in the last section or mentioned, is the maximum displacement. The displacement there varies. You can see here this line varies with distance. That's what makes it a wave. The equilibrium position is here, and the maximum amplitude, either positive or negative, is the maximum displacement. Sorry, the amplitude is the maximum displacement. It is given the symbol A or x0. The wavelength is the distance between two consecutive points that are in phase. They're doing the same thing. So here is the crest of a wave. Next crest is one wavelength. Next crest is another wavelength. Or we can measure from trough to trough is a wavelength. Or we could measure from coming down through equilibrium to coming down through equilibrium. Or going up through equilibrium to going up. It's all one wavelength. But notice that if this is a graph, then this would be a distance, amplitude, and this would be a distance moving along. Looking very similar, but not quite the same thing, here's another graph. The vertical axis actually is the same. It's displacement. Again, amplitude, negative amplitude, maximum displacement. But now our x-axis is time, or t, measured in presumably seconds, but it could be minutes or hours or whatever. And big T is the period. The period you should be familiar with. It's the time for one complete oscillation, generally measured in seconds. Frequency is a related concept, and it's the number of oscillations per unit time, so per second, or we'll give it a special name, hertz. And these two quantities are related. The period equals 1 divided by the frequency, and vice versa, the frequency equals 1 divided by the period. We can use these measurements and these definitions to come up with a bit of an expression for the speed of a wave. Speed of a wave is given the symbol v, or sometimes c, although generally c is reserved for the speed of light. And it's the distance moved by a wave per unit time. It's a distance per unit time, so it's meters per second. It is just speed. Here we have a wave at t equals 0, and we've illustrated for you here one wavelength. In time t, the period, a wave moves a distance of one wavelength. It moves a complete oscillation. We can show that here. Bing. So it moves forward, t equals t. The period, it's moved forward by one wavelength. Remember, t equals 1 over f. Therefore, speed equals distance divided by time. That's a very basic equation. So the distance is the wavelength, and the time is the period. V equals lambda over t. But t, as we've said, equals 1 over f, so v equals lambda over 1 over f. Sort that mess out, and it goes to v equals f lambda. So the velocity of a wave is the frequency of wave, which is waves per second, multiplied by the wavelength, which is the distance of a wave, which kind of makes sense. Any doubts? Best thing to do is to plug some numbers in, have a go, try the calculations. But that v equals f lambda is the basic equation for wave speed. So we've defined wave motion quantities, we've defined frequency, we've defined wavelength, we've defined amplitude, we've defined wave speed, and we've derived the relationship v equals f lambda, wave speed equals the frequency of a wave multiplied by the wavelength of a wave. Thank you very much.